Hey everyone, welcome back to Brainwave, the channel where we dive deep into the mind-bending world of quantum physics without making your brain explode. Today, we're tackling something straight out of a sci-fi thriller. Could a quantum neural network actually cheat Heisenberg's uncertainty principle? Yeah, you heard that right. The unbreakable rule of quantum mechanics might have a loophole. Stick around, because by the end of this video, you'll not only understand what this means, but also how it could revolutionize everything from drug discovery to supercomputers. If you're new here, hit that subscribe button and ring the bell. Let's quantum leap into this. Imagine this. You're Tony Stark in Iron Man, tinkering in your lab, trying to build the ultimate AI. But instead of arc reactors, you're dealing with particles that refuse to tell you where they are and how fast they're going at the same time. That's Heisenberg's Uncertainty Principle in a nutshell. The quantum world's way of saying, you can't have it all. It's like trying to catch a slippery fish in the dark. Grab its position, and its speed slips away. This principle has haunted physicists since 1927, limiting what we can measure in the subatomic realm. But what if I told you a team of scientists just proposed a way to outsmart it using a quantum neural network? It's not magic. It's math, randomness, and a dash of machine learning genius. This breakthrough, detailed in a recent New Scientist article, could flip quantum computing on its head. Excited? Let's break it down step by step. First off, let's rewind to the basics, because quantum stuff can feel like entering the upside down from Stranger Things. Familiar, yet totally weird. Heisenberg's uncertainty principle isn't about bad tools or clumsy scientists. It's a fundamental law. For particles like electrons, if you nail down their position precisely, their momentum, basically speed and direction, becomes fuzzy, and vice versa. Why? Because at the quantum level, everything's a wave of probabilities until you measure it, collapsing that wave. It's like in the Matrix, where reality bends based on observation. Real-life example. In MRI machines at hospitals, this principle helps create detailed body images by manipulating magnetic fields around atoms. Without understanding uncertainty, those scans wouldn't work. But it also caps how much info we can squeeze from quantum systems, slowing down tech like quantum computers. Enter the hero of our story, the quantum neural network, or QNN. Think of it as the love child of quantum computing and artificial neural networks, the kind powering Netflix recommendations. In classical neural nets, data flows through layers of neurons that learn patterns. QNNs do the same, but with qubits, those quirky quantum bits that can be 0, 1, or both at once, thanks to superposition. The twist in this new research? Randomness. Yeah, injecting chaos on purpose to beat the system. The idea comes from Duanlu Zhou and his team at the Chinese Academy of Sciences. They published a theoretical paper showing how a QNN can measure incompatible properties, like position and momentum, more accurately by randomizing the process. Here's how it works. Instead of straightforward measurements that clash due to uncertainty, the network applies a sequence of random quantum operations to the system. It's like shuffling a deck of cards multiple times in unpredictable ways, then using stats to figure out the original order. Picture this in a Hollywood scene. In Avengers Endgame, when Scott Lang, Ant-Man, navigates the quantum realm, time and space get all jumbled. That's kind of what happens here. The randomness scrambles the quantum state. But over many runs, you collect data and use machine learning to unscramble it. The result? You extract precise info about multiple properties without directly violating the principle. It's not cheating like hacking the matrix. It's more like finding a backdoor through clever stats. Why does this matter? Let's get practical. In quantum chemistry, simulating molecules is a nightmare because classical computers choke on the complexity. Remember the protein folding breakthrough with AlphaFold? That's AI tackling biology. Now, imagine QNNs speeding up simulations of drug molecules interacting with viruses. Real-life impact. During the COVID-19 pandemic, scientists used quantum-inspired algorithms to model spike proteins. With this randomness trick, we could design vaccines faster next time. Or think about batteries. Quantum sims could optimize lithium-ion structures, leading to electric cars that charge in minutes, not hours. Quantum tech like this could slash R&D time from years to months. For instance, benchmarking qubits in a quantum computer usually requires tons of measurements. With a randomized QNN, you could do it quicker, like streamlining a factory assembly line. Critics, like Robert Huang from Caltech, point out it needs testing against other methods. Quantum hardware is noisy. Think of it as a temperamental sports car from Fast and Furious that overheats easily. Randomness adds iterations, which might amplify errors on current devices from IBM or Google. Remember in Inception when they layer dreams within dreams? Quantum layers work similarly, stacking operations to process info. But add randomness, and it's like randomizing the dream levels to extract secrets without waking the mark. Cool analogy, right? In real life, this mirrors how nature uses quantum effects. Photosynthesis in plants exploits quantum coherence, particles trying multiple paths at once to find the best way to convert sunlight. Uncertainty limits direct study, but a QNN could model it better, inspiring more efficient solar panels. Imagine powering your home with tech mimicking a leaf. That's the future we're talking about. Diving deeper, the math behind this is fascinating. Traditional quantum measurements are deterministic, fixed steps. But Zhou's team proved that by randomizing unitaries, fancy quantum rotations, you can statistically infer properties. It's like polling a crowd. One vote is uncertain, but thousands reveal the trend. For qubits, this means measuring entanglement or coherence without the usual trade-offs. In TV terms, it's like Sheldon from The Big Bang Theory explaining string theory. Complex, but with the right tools, solvable. Potential downsides? Scalability. Current quantum computers have 100 to 1,000 qubits. Fault-tolerant ones need millions. Randomness requires running the network many times, which could be computationally expensive. Plus, noise from the environment, like cosmic rays or vibrations, could mess up the stats. Real-world example. Google's Sycamore chip achieved quantum supremacy in 2019, but it was for a niche task. Integrating QNNs might push us toward practical supremacy, like cracking encryption or optimizing traffic in smart cities. Let's tie this to everyday life. Ever used GPS? It relies on relativity corrections, a cousin of quantum effects. Without them, your Uber would be miles off. Quantum neural nets could enhance AI and self-driving cars, predicting pedestrian movements with quantum speed simulations. Or in finance, modeling stock markets as quantum systems for better risk assessment. During the 2008 crash, better models might have softened the blow. As we wrap up, remember this isn't about breaking physics. It's about working smarter within it. The uncertainty principle stands, but tools like QNN let us peek around corners. If experiments confirm this, we're looking at a quantum renaissance. Want to dive deeper? Check out the New Scientist article linked in the description. What do you think? Is this the next big thing, or just hype? Drop your thoughts in the comments. Like if quantum blows your mind, and share with a friend who's into sci-fi. Thanks for watching, and I'll see you in the next quantum adventure. Peace out.